Hello, I'm Tony Auerbach, and this is the first in a series of 3 videos on the subject agonist efficiency. In brief, efficiency is the correlation between agonist affinity and agonist efficacy, and it can be used to classify agonists, interpret dose-response curves, and understand the biophysical mechanisms that undergird receptor activation. I have divided the presentation into 3 parts. The first video will be about the basics of how agonists activate receptors. The second part will be about efficiency per se. And the third part will be about the energy linkage that determine efficiency. So in a sense, this is like a video pamphlet, the 3 of them together in the form of an introduction section, a results section, and a discussion section. I won't say much about methodology, but that information will be in the citations that I've given as a year, the first author, and a keyword from the title. So let's start with the basics of receptor operation. The topics I will consider are dose-response curves, thermodynamic cycle, equilibrium constants, unliganded activity, and I will also address 2 frequently asked questions, the second of which pertains to voltage-gated ion channels. I'm going to start with the dose response curve or concentration response curve, which is something we're all familiar with. There's a low concentration asymptote that is close to 0. There's a high concentration asymptote that is somewhere less than 1, and then there's a midpoint that locates the curve on the concentration axis. We're going to be talking about energy efficiency, so I want to relabel these axes as energy in and energy out. So you're pouring energy into the system in the form of an agonist concentration, and you're recording energy out of the system in the form of a response. That can be quite complicated, but at its base has a conformational change in the receptor. And it is this curve that we're going to use as the window for understanding agonist efficiency. So the receptor I will be talking about is a subtype of nicotinic acetylcholine receptor, which is a ligand-gated ion channel. These receptors have 5 subunits arranged around a central ion channel. The molecular weight is about 300,000 in total. In the extracellular domain, there are binding sites for the neurotransmitter and the agonist that we will be considering. In the transmembrane domain at the center, there's a narrow region of the pore called the gate, which can switch on and off to either allow or prohibit ion flow through the channel by either connecting or separating the extracellular and intracellular water compartments. And there is also an intracellular domain, which is not shown in this picture. The subtype of nicotinic receptor that we will be considering is the muscle type. And in adult muscle, there are 2 binding sites shown here in red that are equivalent and independent. And equivalent means that they have similar binding properties for the agonist that we will be talking about today. And they are independent, meaning that those binding properties remain the same regardless of whether the companion site is occupied or empty, filled with water. There is another type of muscle receptor that's present in embryonic muscle. And here, there's a subunit switched, and the 2 binding sites are no longer equivalent. They are still independent, but they have different binding properties. But we're going to be talking mostly about the adult type receptor. Now, I will say the adult type receptor has been a fabulous model system for understanding receptors in general. Many fundamental concepts of pharmacology came from studying this as a prototypical receptor. Those concepts include the concept of a receptor, which was first associated with the muscle acetylcholine receptor, affinity, efficacy, allosteric proteins, as well as some technical advances, including single channels and cryo-EM. These were all first done on acetylcholine receptors, so it is a very good model system. All receptors are allosteric proteins, and I'll define an allosteric protein as one that has two native states uh, that have different functional outputs and different sensitivities to environmental energy input. And here the energy input is binding from a ligand binding. So down below are shown potential energy surfaces or energy landscapes in which the native states are represented as energy wells or points of stability. And if you look at the left, this is the energy diagram, energy landscape without any agonist present. The left well is called C for closed channel, and the right well is O for open channel. C has a low affinity for agonist, and O has a high affinity for agonist. And you can see that without ligands, O is less stable than C, which means the probability of being in O is going to be smaller than in C. The situation changes when you add agonists. On the right side, you can see that the stability of O is greater than that of C when there's a ligand present at the binding site. And therefore, the probability of being open is going to be higher than it was without any agonist. Now, why does this happen? It's simply due to the difference in binding energy of the two states. When the binding site is in its C conformation, there is only a little bit of energy stabilization provided by the agonist. But when the binding site has spontaneously switched to O, the agonist provides significantly more stabilization energy. So this turns an uphill reaction without agonist into a downhill reaction with agonist. Now there's another state present in these diagrams, which is the barrier that separates C and O. This point of instability is called the transition state, and it too can bind agonists. There is agonist binding properties to the transition state, and in acetylcholine receptors, the transition state agonists bind to the transition state with the same avidity as they do to the open state. So you get the same stabilization of the transition state as you do to O. So this, in effect, lowers the barrier that separates C from O, easing the pathway from C to O. So you imagine the system is in C, spontaneously trying to get from C to O, but being frustrated over on the left without ligands. But when a ligand has bound, the transition state energy also is low, and therefore the pathway to open is eased, and the probability of being open goes up. So in essence, in all receptors, agonists activate receptors because they bind more strongly to the active conformation of the binding site. And in any receptor in which the agonists elicit a rapid response, you could guess that the transition state energy also is lowered. The energy landscape representation of an allosteric protein can be turned into a standard state model, which takes the form of a cycle. The vertical lines of the cycle here represent the conformational change from C to O, which is called gating, and which is global. And the horizontal lines represent the deposition of stimulus energy into C, which means binding of agonist to C and binding of agonist to O. These are the equilibrium constants for the cycle. L is for gating, and Kd is for equilibrium dissociation constant. The subscripts represent either 0 and 1 agonist or to closed and open channels. So for every receptor, there are two affinities, low affinity to C and high affinity to the active state. But the word affinity is usually applied only to the low affinity binding constant because it is in the main activation pathway. And there this shows that the opening rate constant is the only difference between the L1 and L0, the main difference between L1 and L0. So this is the core model for binding horizontal and gating vertical. But there are extensions, of course. Now there's going to be two agonist binding sites in acetylcholine receptors, so to incorporate that, you would have to add a second cycle to the right. In addition, acetylcholine receptors and all receptors can enter an inactivated or desensitized state that has a high affinity for ligands like O, but a closed channel like C. And that would be modeled by adding another plane to the back. But that's a topic for another seminar. Right now, we're just going to focus on binding and gating, and we will make sure to eliminate desensitization from our accounting when we do the experiments. In 1840, a Swiss chemist, Germain Henri Hess, was working in St. Petersburg, having been brought there by Catherine the Great, had built himself a new calorimeter and was measuring the heats of hydration of sulfuric acid, and made the following observation. A combination having taken place, the quantity of heat evolved is always constant whether the combination is performed directly or whether it takes place indirectly and in different steps. This empirical observation was formulated into a law known as Hess's law, and this was done before the conservation of energy was well established. So the implication of Hess's law to the thermodynamic cycle is that getting across the diagonal of the cycle should require the same energy whether it takes place by the clockwise or the counterclockwise paths, which means that the product of the equilibrium constants of the two paths should be equal, which leads to the equation shown to the right highlighted in green. The ratio of the gating equilibrium constants is equal to the ratio of the binding equilibrium constants, and that ratio is called the coupling constant. For a two-site receptor, the equation would be L2 over L0 equals the coupling constant squared. So recently, some people have suggested that in ion channels, the input of energy from the ion flow may obviate Hess's law. So what we did is we decided to test this by measuring each of the four equilibrium constants independently. And we found that for 4 different agonists at 3 different binding sites, the green equation was correct. So in acetylcholine receptors, there is no significant external energy. Everything that happens does so spontaneously, driven by temperature alone. So it's likely that in all ion channels, the flow from the current is not as significant, and although in other receptors there is possibility of external energy coming in the form of mechanical deformation of the membrane or metabolic events. We now want to relate the equilibrium constants of the cycle to the 3 parameters that are estimated from a dose-response curve, namely the minimum, maximum, and EC50, and these are estimated by fitting the data points to some empirical function such as the Hill equation. The term efficacy is the difference between the maximum and the minimum, but since the minimum is the same for all agonists and is close to 0, generally the high concentration asymptote is taken as an indication of agonist efficacy, and potency is another word for EC50. These 3 parameters can be used to calculate the 4 equilibrium constants of the cycle as follows. The L2, the gating equilibrium constant for a fully liganded receptor, is only a function of the maximum. L0, the constitutive gating equilibrium constant, is a function only of the minimum. KDC, the low affinity binding constant, is a function of EC50 and the maximum, and KDO is a function of everything, all 3 parameters, and the green equation. So you can get all 4 constants from a simple fit of a Hill equation to a dose-response curve. So let's do this for some real-world data. The points are single-channel open probabilities, PO, from adult-type mouse muscle acetylcholine receptors fitted by, and the curves are fitted by the Hill equation for 3 different ligands: the neurotransmitter acetylcholine, epibatidine, which is a frog toxin, and tetramethylammonium, which is a very small molecule. You can see that the 3 agonists have 3 different maxima and 3 different EC50s, but the minimum was taken to be the same for all 3 agonists. Now, this was not estimated. That value of 7 times 10 to minus 7th was estimated independently, and I'll show you how we did that later on. That did not come from analysis of the dose-response curve. The constitutive opening is way too small for that. So we take these maxima and we take these curves and we fit it to get a maximum in EC50, from which we calculate L2 and then KDC and then KDO, and you can see that the low affinity binding constant to the closed channel is in the micromolar range, and the high affinity binding constant to the open channel is in the nanomolar range. So we can take the ratio of those two constants to calculate the coupling constant, and these are the values we get in factors of 1,000. That means each acetylcholine increases the gating equilibrium constant by a factor of 5,800, or if two of them together would be a factor of whatever that is, 36 million, 34 million, above the equilibrium the unliganded gating equilibrium constant. The coupling constant is a quantitative measure of how partial the agonist is. So this is a list of coupling constants obtained by calculating the square root of L2 over L0 for a number of choline derivatives. There's a wide range that ranges from 6,000 for ACH. Choline, in which the gray box here would be a hydrogen only, is reduced to 256, and betaine, in which the gray box is a carboxyl group, is reduced to 5. Now, I won't go through these all, but just to let you know, there's a very wide range of coupling constants. Another way to quantify the coupling constant is on a log scale. Energy is proportional to the logarithm of the coupling constant, the energy from each ligand, where R is the gas constant and T is the absolute temperature. And that gives you the energy from each ligand in the units kcals per mole. So you double this if you wanted to do it for a whole receptor. So agonists are like earthquake energy on a scale from 0 to 10, with a negative number meaning favorable towards opening, agonist. An antagonist is a ligand that has a coupling constant of exactly 1, which means the energy is exactly 0. And an inverse agonist is a ligand that has a coupling constant less than 1, which translates to an energy of a positive energy. And we also measure the rate constants for opening and closing for these series of ligands. And the plot to the right is a log-log plot of the opening rate constant as a function of the gating equilibrium constant. And what that is, in effect, is the ratio of the two green bars of the energy landscape shown above, the bar for the transition state divided by the bar for the open state. And that ratio is called phi, and phi, the subscript G, means the phi value for gating. And you can see here that the change in the log opening rate was equal to that of the change in the gating equilibrium constant almost completely. So those two bars have the same height, which means that the transition state is stabilized to the same extent as the end state. So all these agonists fall on that same correlation plot. And I want to highlight water here, which the unliganded opening and equilibrium constants also fall on the same plot, which means water is the dividing line between agonists and inverse agonists. Anything to the right of water is an agonist, and anything to the left of water is an inverse agonist. And we haven't found any inverse agonists yet of acetylcholine. And I'm going to use this plot later in the third lecture, this correlation plot. This is how I tend to think of the thermodynamic cycle of a receptor. That is, I put most emphasis on the unliganded gating constant, L0. And I think I'm unusual in this regard because most people think of it in this way. They don't think of it as a cycle at all, but they think of it as a sequential steps of agonist binding followed by the conformational change. And that is because these constants are the only ones that are necessary to calculate a dose response curve and a synaptic current flow. And in the next slide, I'm going to try to justify why I think L0 deserves more attention. Why is L0? Why do I put L0 so important? Why bother measuring L0? So I'm going to give you 3 reasons why it's important to measure L0. First is the coupling constant. If you want to be quantitative and say how partial or agonist really is, you need to know L0. You only have to measure it once, and then it's just from the ratio of L2 or L1 to L0, you can calculate the coupling constant. So it's important for quantifying agonist action. It's also important for understanding dose-response curve. So down below, I have rearranged the green equation to show you how L0 affects the dose-response curve. So we know that I've showed you that L2 affects max, and it can also affect EC50. That was in the EC50 equation. So L2 and L2 is determined by L0. So the ratio of binding equilibrium constants, the coupling constant, is something that's happening strictly at the binding site. But L0 is influenced by all manner of perturbations to the protein. So the structural components of the system determine L0. That is the amino acids, so a mutation can change L0. The subunits will change L0, and elements in the membrane will change L0. Also, there are stimuli that affect L0 that may or may not be under your experimental control. The voltage will change L0, their mechanical effects will change L0, as will allosteric modulators. That's how many allosteric modulators work. Finally, there are post-translational modifications that affect L0. I've only listed 2 here. So all these things change 0, and when you change L0, you're going to change L2. When you change L2, you're going to change your dose-response curve. So on the right are 3 dose-response curves, one for the wild type and 2 others following point mutations that do nothing more than change L0. These mutations do not change KDC or KDO. They just change L0. They increase L0. And you can see as you increase L0 more and more, you shift the EC50 to the left, and you also raise the maximum, although you cannot see that in here because the maximum of the wild type is already so high. It's 0.96. So it goes from 0.96 to 0.99 to 0.999. You can't measure that in the dose-response curve. So you see a shift in the dose-response curve, and it's easy to think that you're changing the affinity of the receptor, when in fact you're changing neither of the 2 affinities. All you are doing is changing L0. So it's important to keep that in mind and don't interpret a shift in the dose-response curve as a long-range allosteric effect on the protein. These 2 mutations are very far from the binding site, and they do not affect affinity. There is a long-range effect, but the long-range effect is mediated through L0. So it's important to know L0 can change your dose-response curves. Now, it comes up, why does a mutation L0? And that's another topic for another seminar. But basically, let's take the S450W. The side chain at that position is sort of like an agonist that has a differential stability in closed versus ocean. Just like the agonist gave different binding energies in C and O, S has a different effect on the energy wells in C versus O. And when you switch that to W, it changes the relative difference in those energies. So W is more stable in O compared to S. So that's why you get that. It's a local effect. It has nothing to do with energy propagating through the protein. It's just that side chain is more stable in O compared to C. And the third reason now to measure O is because it's useful in engineering responses. So as you can see from the green equation, if you change O, you change max in EC50. And that means if you want to take a weak agonist and make it stronger, or a strong agonist and make it weaker, you can just change L0. You can reverse the effects of voltage and some of these other stimuli down there. If you don't like what they're doing, you can engineer your L0 to be what you want, to put everything in the sweet spot of the patch clamp, or whatever instrument you're using to record responses. I just want to show one quick other example, which is you can also engineer the transition state, not only the equilibrium constant, but the transition state. So temperature only affects the transition state, and by judiciously adding mutations that change the transition state, you can engineer the temperature dependence of your response. These are simulated synaptic currents to the right, and we can speed up a response that is normally slow at 10 degrees. So, in other words, for those three reasons, it's important to measure L0. So, in the final topic, how do you measure L0? I mentioned that you can't get it from a dose-response curve because the response is so small, but there have been 4 ways that have been used to measure L0. Each of them has its certain advantages and certain disadvantages. I won't go through these in detail, but I'll just briefly go through each one of them. One way is by direct measurement of the constitutive response. It's very simple conceptually, but very difficult technically because constitutive responses are quite small, and you need to know the number of receptors contributing to that response. So it's very technically difficult to do. That was first done by Meyer-Jackson in 1986 in acetylcholine receptors, again, the first receptor. Another way to do this is by extrapolation from the effects of mutations on L2 versus L0. This is very accurate, but it's a little bit abstract conceptually. You have to use the Green equation, and it is labor intensive. You have to make lots of mutations and calibrate their effects on a weak agonist. A third method that we have used is just by measuring single sites, gating with only one active binding site. The simple relationship is L2 over L1 is equal to L1 over L0. So if you know L1 and L2, you can calculate L0. It's very simple conceptually, but it's not generally applicable. You have to be able to measure a receptor that has only one active binding site, and that can be difficult to construct. And the fourth way, which I think is the best way, is from an efficiency plot, which is an extrapolation from a series of agonists of a plot of the log-log plot of KD versus L2. So you only need wild-type receptors. You get a very accurate estimate, but it is abstract. It requires both the Green equation and a new equation I will show in the next video, the pink equation. So I think it's the best way to go, and I will go into this method in detail in the next video. These are the values of L0 for adult and fetal type nicotinic muscle receptors. The values are the same in both human and mouse receptors. The fetal type has about a 10 times lower level of constitutive activity. We don't know the physiological reason why this has come to be, but presumably it's because the gamma subunit side chains, some of them, maybe one, maybe several, have evolved to be more stable in C compared to O relative to those in epsilon, and therefore reduce the level of constitutive activity. So these values are the same for all agonists, but they do change with mutations, and they will also change with voltage. And the voltage sensitivity is differential between those two. So next I want to that's the end of the discussion of the basics of receptor operation, and I now want to go on to address 2 frequently asked questions. The first question I am often asked is the following: aren't the 2 acetylcholine receptor binding sites different? I recall reading papers, I thought it was established that they are different. The answer to this question unequivocally is no. They are the equivalent and independent. So I now want to explain why the source of confusion. The first receptors to be studied in detail were the fetal type receptors, and as I showed earlier, that in fetal type receptors, the 2 binding interfaces are indeed different. The alpha-gamma interface has a higher affinity for ligands than does the alpha-delta interface. So it was natural to assume that this was also the case in adult type receptors. But nature is tricky. In addition to the binding events, there is another closed interval, short-lived closed interval present in single-channel recordings that reflects entry into a short-lived desensitized state, which people have ignored, but people focus on the long-lived desensitized states. It turns out there are 4 desensitized states, one of which has a lifetime of about a millisecond and is present at all concentrations to about 2% of the events. That's shown in the histograms on the lower left. So when this event is not explicitly included in the model, it gets put into the blue arrows. But the correct model to use is one which has explicitly a short-lived desensitized state. And when that is done, then the 2 binding sites turn out to be equivalent. And that was confirmed unequivocally when we measured the binding to individual binding sites in that 2017 paper. The 2 for the agonists that we're talking about here, that the binding sites are independent and equivalent. So in the citations, I've put an X next to a paper that is one of my more highly cited papers, in which I'm a co-author, where it says that the binding sites are equivalent. That is incorrect. That is a mistake. Please do not cite that paper if you want to cite it for the equivalence of the binding sites. The good news is that you can just ignore the blue equilibrium constant and just focus on the red ones, because the red constants, when you use the wrong model, give you the correct values. The second question I would like to address is about voltage-gated ion channels. The observation is that as you hyperpolarize the system more and more, the probability of being open gets smaller and smaller without any apparent asymptote. And that has been interpreted as arguing against the allosteric model. And I would like to show you how I think voltage-gated channels indeed do fit nicely in with the standard version of an allosteric system. So again, this is the thermodynamic cycle. The vertical lines represent the global isomerization of the protein without and with stimulus energy, and the horizontal lines represent stimulus energy deposited into C and O, and in this case the stimulus energy is voltage. These are the energies of each step of the thermodynamic cycle for a voltage-gated channel. The stimulus energy is charge times voltage, and the gating energy is just minus the log times the equilibrium constant. The gating currents are part of the global isomerization and are contained within the vertical gating arrows. They are not in the horizontal arrows, they are in the gating arrows. And if you wait until the 3rd lecture of this series, if you make it that far, then I will describe an analogous event inside of acetylcholine receptor gating called hold. For returning to the energies, you can connect the diagonal by adding the sums of the energies according to either route, clockwise or anti-clockwise, and that gives you the following equation for the energy of the coupling constant, the log of the coupling constant. So the energy of the coupling constant is the minus voltage times the difference in charge, and that number, hyperpolarization, meaning negative voltage, makes that energy positive. Positive energy is like an inverse agonist. That stabilizes the closed state. Adding positive voltage would make this coupling constant energy negative, which makes it like an agonist and increases the open probability. So you can make the open probability arbitrarily small or arbitrarily large by adding negative or positive voltage without saturation. So the lack of saturation just means that you're making the coupling constant larger. It is not reflective on L0. These are the people who did the work that I described in this first part of the lecture series. At the end of the 3rd video, I will give a much more extensive acknowledgments.